Welcome back to the preparation for the math placement exam. If you are going to enter into your first semester in college and you have several math courses that you need to complete and you're hoping to be placed into Calculus 1, then it is smart to prepare for the math placement exams. This is part 2. At the end of part 1, we were working on this problem. And so I wanted to go ahead and do this problem one more time. I had a pencil malfunction. As you can see today, I have a good old-fashioned number 2 orange pencil. So we won't be having the same issues we had last time. Okay, so we're going to be evaluating this expression, and then we're also going to simplify a couple of expressions, simplifying them to the point where the final expression does not have a negative exponent associated with it. So we'll do that after we look at this. All right, so a couple things we want to remember from the end of part 1. This relationship, x raised to the m over n exponent. This is equivalent to the nth root of x to the m. The denominator of my exponent is the root number, and the numerator of my exponent, it sticks with the base, okay? And you might think, well, ours is negative in this example, the same thing, right? X to the negative m over n is equal to the nth root of x to the negative m. The next step we take here is another relationship we spoke about last time, where if you have x raised to the negative m, you can then write 1 over x to the positive m. Okay, those are the 2 relationships that we want to keep in mind here. So let's go ahead and evaluate 16 to the negative 3/4. So I'm just going to follow the rule above. 16 to the negative 3/4 is equal to the 4th root, 4 is our denominator, the 4th root of 16 to the negative 3rd. We want to go ahead and replace our 16 to the negative 3rd with 1 over 16 to the positive 3rd. Okay, and so we have the 4th root of 1 over 4,096. Now, we can take this a step further as to how a root is applied to a fraction, and that's what I want to show you here. If I'm taking the root of a fraction, then I can also think of it as the root, that root of the numerator divided by that root of the denominator. And so the 4th root of 1 divided by the 4th root of 4,096. And the 4th root of 1, this equals 1. The 4th root of 4,096, you can think of this as, well, what number, if I multiply it 4 times, I'll get 4,096. Okay, we're assuming that you do not have a calculator for this exam. So here is where your mind then should go. Okay, well, what times what times what times what, all the what's being the same number, equals 4,096. And so eventually you will see that 8 times 8 times 8 times 8 does equal 4,096. So the 4th root of 4,096 is 8, and our final answer is 1/8. Let's go to simplifying each expression. Write your answers without negative exponents, okay? The first one I want to look at is the square root of 200, subtract the square root of 32, okay? I am going to go the route of this first way of thinking. This will be the individual that looks at 200 and immediately thinks 100 times 2. And then they look at 32 and they immediately think 16 times 2. Now let's explain a little bit here. If I'm looking for the square root of a number that perhaps isn't a perfect square itself, and by perfect square, let me give you some examples of some perfect squares. I have 1 times 1, that equals 1. 1 is a perfect square. 2 times 2, that equals 4. 4 is a perfect square. 4 is a perfect square. 1 is a perfect square because I can multiply a number twice to get that number. The product of one number multiplied by itself once gives me that number. So 4 is a perfect square. Well, okay, what's the next perfect square that we're familiar with? 9 is a perfect square. 3 times 3. I think you get what I'm doing here. What's the next perfect square? 16, right? These are some familiar perfect squares that you should be familiar with whole numbers. 5 times 5, 25 is a perfect square. 6 times 6, 36 is a perfect square, okay? So let's say the person here, they know that we're dealing with a square root. It's not written, but it's implied. These are square roots. And so we're looking for a factor of 200 that is a perfect square. And we're looking for a factor of 32 that is a perfect square. And just in case you're not familiar with what factors are, I'm going to write out this expression in English. A factor times a factor equals the product, right? So if the product is 200, what times what equals 200? And since we're dealing with square roots, is there a situation where I can multiply the same number to itself and get 200? Well, there isn't, but a factor of 200 is a perfect square. So if I do 100 times 2, guess what? 100 is a perfect square because 10 times 10 equals 100. And if I'm looking for a factor of 32 that's a perfect square, I will think of 16. I could think of 16. We'll look at an example of someone who may think differently. I could think of 16. 16 is a perfect square, 4 times 4. So now that I've identified factors of 200, and one of those factors being a perfect square, and then I identified the factors of 32, one of those factors being a perfect square, now I can go ahead and proceed with simplifying this expression. So my square root, being that I'm multiplying these two numbers together underneath the square root can apply itself to the 100 and leave the 2. So the square root says, hey, 100, you're a perfect square. Let's go ahead and process you. Boom, the 10 comes out from underneath the radican, the 2 stays underneath. And then the square root looks at the 16 and the 2, 16, hey, you're a perfect square. Come on out. So the 4 comes out, right? Because 4 times 4 is 16. And notice we're taking the square root and we're only focusing on the positive output of the square root. The square root of 100 is positive and negative 10. Positive 10 times positive 10 is 100. And then negative 10 times negative 10 is 100. But when we're simplifying these expressions, we're going to focus on the positive output of the square root of 100. So that's positive 10. The 2 is not a perfect square, so it stays underneath the radican. And then minus, we're going to take the positive 4 here in our processing the square root of 16, and the 2 stays here. Notice here that what is left underneath the radican is the same, 2 and 2. And that's a great sign that we have simplified correctly, okay? There's a 2 left underneath, 2 left underneath, excellent. We have a 10, we have a 4. So think of this as now we have 10 times the square root of 2 minus 4 times the square root of 2. Another way to say this is we have 10 square roots of 2 minus 4 square root of 2. 10 times square root of 2 minus 4 times square root of 2 is equivalent to 6 square roots of 2. Okay, and this is our final answer. Now, let's say that you thought of a different you thought of a different square root underneath here. So let's go ahead and pull this out. So remember, we started off with the square root of 200 minus the square root of 32, okay? The square root of 200 minus the square root of 32. Now, let's say you look at the 200 and you're thinking, okay, I need a factor that's a perfect square. Boom, 25. Let's say 25 popped into your head. You know that there's 4 25s in 100. So then you know there's 8 25s in 200. And you said, oh, great, 25 is a perfect square. Let's go. And then let's say you looked at 32 and you thought, 4. 4 is a factor of 32 and 4 is a perfect square. Excellent. So I'm going to do the square root of 4 times 8. Okay. Now, if you were to just go ahead and from this point of your calculating, you did 5 times the square root of 8 minus 2 times the square root of 8. And then you got 3 times the square root of 8. Though this is equivalent to the square root of 200 minus the square root of 32, it is not the most simplified version of the square root of 200 minus the square root of 32. And that is, it's not the most simplified because 8 still has a factor that is a perfect square. 4. I can still separate this 8 into 4 times 2, 4 times 2, okay? And so this is something you'll have to recognize if you go with a smaller perfect square underneath here in your first step. If you go with 25 and 4, you must recognize that, yes, 25 times 8, the square root of that is equivalent to 5 times the square root of 8, and you'll get minus 2 times the square root of 8. And yes, the 8s are the same underneath the square root symbol, but it is not the most simplified. We still have a perfect square underneath the square root. And so 3 times the square root of 8, that's going to get you an incorrect answer. It'll say incorrect. It's equivalent, but it's not the final answer they are looking for, okay? So let's go ahead and process this 8, okay? And let me show you that you can still get the right answer with taking this as your first step. There's just extra steps. So we see that we have a perfect square of 25. Let's keep that. And then let's notice that 8, one of the factors of 8 is also a perfect square. So I'm going to write 25 and then I'm going to write 8 in its factored pieces with 4 being its perfect square. So 25 times 4 times 2. And I'm doing the same thing here. Yes, 4 times 8 is 32. 4 is a perfect square, but there's another perfect square. The other perfect square, 4 times 2 is 8. Okay, I hope that you are following me. Now I can go ahead and process each of the perfect squares. The square root of 25 is 5, and the square root of 4 is 2. So the 5 and the 2 come out from underneath the radicand, and a square root of 2 is left. And then over here, the square root of 4 is 2. The square root of the other 4 is 2. And what's left underneath is another 2. This is a way to think about it. You just have to recognize and remember that we're trying to simplify and recognize that this 8 has to be processed, and that when you are processing the perfect squares, we are focusing on the positive of the output of the perfect square. And we're able to do this because we're multiplying this number times this number times this number. As you go higher up in math, we'll see what magic we can make and do when we're taking the square root of things that are being added and subtracted. It's still a matter of factoring something out that is a perfect square being multiplied, okay? But here, just know we're multiplying each of these. And so I can process each of these separately if that's the path that my brain took during the exam, okay? And so now we see here that once I've I have the positive 5 from the square root of 25, the positive 2 from the square root of 4. I have a 2 left underneath, minus square root of 4, square root of 4 again, 2 with a 2 left underneath. 5 times 2 outside of here is 10. 2 times 2 outside of here is 4. Now we have a number left underneath the radicand that there's no factor of 2 that's a perfect square, so that's as simple as it gets. And then our final answer is 6 times the square root of 2. Okay, so you have two routes you can go here. One obviously has more steps than the other. And this is why it's important to practice and to prepare for this exam, because if you were thinking more smaller perfect squares, you add more steps, but the more practice you do, you'll train your brain to think of those bigger perfect squares that might work. All right, let's look finally at the last problem for part 2 of this series. We're going to, again, simplify this expression and make sure that our final simplification does not have negative exponents. And let me just say here really quickly, this final answer does not have a negative exponent. I can rewrite this as 6 times 2 to the 1/2. 1/2 is positive, it is not negative. So we have definitely simplified this expression, and we have written our answer without the negative exponent. Okay, square root of 2, that is equivalent to 2 raised to a power of 1/2. 2 with an exponent of 1/2. All right, let's take a look at this last problem. And I'm going to cover up the other part so we can discuss this. Okay, so we have this number here. Okay, this is a number 3 times a to the 3rd times b to the 3rd. And then we have this number here, 4 times a times b squared, that being raised to an exponent of 2. All right, I'm going to go the direct route first, and then I'll take a more complicated yet still very correct route next for just the different types of ways you can think about it. So here I'm going to go ahead and first distribute the power that is on the outside of the parentheses. There's a 2 here. They don't have a number written here, but tell me what number is here? What number is implied? There's a 1. There's a 1 there. And so we're going to apply those exponents first. That takes us to this next line of math, 3. And I put the multiplication symbol in between just so that you know that if I have a coefficient here sitting in front of my variables with different exponents, this number here in front of the letters, as you may think about them, but they are variables, they can vary. And there's no math operation. If I cover the parentheses, there's no math operation, but they're sitting next to each other. That means we're multiplying them, okay? And so I just wanted to notate that down here with this little tiny dot. So it's 3 times a cubed times b cubed times, okay, this parentheses times parentheses, this times this. This happens to be squared. So then it's this 2 is going to apply itself to each of the terms in this expression. So 4 raised to 2, a to the 1st power raised to a power of 2 now, and then b squared becomes b to the 4th power. Okay, we'll look at that in more detail when I look at the next way to think about this. Then we're going to go ahead and put our like terms next to each other. 3 times 4 squared, 3 times 16. I'm going to move our variables a near each other, a cubed times a squared. And then I'm going to move our variable of b's, these terms next to each other, b cubed times b to the 4th. Doing this just to organize my thoughts. If I'm trying to combine like terms, then I just want to see the like terms that I have. You know, what are these like terms? Okay, I'm looking for things that are either integers or these numbers here. And then I'm looking for those variables, those bases that are like variables that I can combine. Okay, so the next step here is then to just go ahead and recall one of the rules that I'm going to talk about more here later on in a few seconds. I'll go ahead and combine these like terms. So 3 times 16 is 48. A cubed times a squared is equivalent to a raised to a 3 plus 2 exponent. B cubed times b to the 4th is the same as b to the 3 plus 4. And our final answer is 48 times a to the 5th power times b to the 7th power. Now let's look at this in more detail and explain a little bit about what we did here, okay? Another way that someone could have thought about this, or another way to think about this, if what we just looked at really, it kind of doesn't make any sense, okay? So let's start from the top. I went ahead and wrote all of the implied exponents. Okay, the 3, there was just a 3. They didn't put an exponent of 1 there, but the 1 is there. On the parentheses, they didn't put an exponent right here, but a 1 is there. On the 4 and on this a, there were no exponents, but a 1 is there. And then we had b squared, and this parenthetical was raised to the 2nd power. This is the rule that we are incorporating first in this first step. If you have something inside the parentheses and whatever's inside of there, if what's inside there has a power of m, and then you're raising that to the nth power, it's the same as multiplying these two exponents, okay? And so I wrote that out right here. This expression raised to a power of 1 is the same as taking each of those terms and multiplying their exponents by this exponent. So this is 3 raised to 1 times 1. This is a raised to 3 times 1. This is b cubed. This is b raised to 3 times 1. Okay, looking at this expression, it's got parentheses around it. All of this is raised to a power of 2. Then it's going to be 4 with an exponent of 1 times 2. 1 times 2. A with an exponent of 1 times 2. And b with an exponent of 2 times 2. You see here, we're incorporating this here. That is how I ended up here with 3 to the 1st power times 4 to the 2nd power, a to the 3rd power, a squared, b cubed, b to the 4th power. I can organize terms that I'm multiplying in any order that I want. Okay, that is the commutative property. It doesn't matter if I say this times this times this times this times this times this, or if I say this times this times this times this times this times this, it doesn't matter, I'm gonna get the same answer. I'm organizing them so that you can see what needs to be simplified and how we can simplify them. Now, I want to take this line of math a step further to help those who are trying to understand, well, how does this work? If I have a to the m power times a to the nth power, how is it that this is equal to a to the m plus n? Well, let's go ahead and write everything out. So we got, this is 3, this is times 16. Here's a cubed written the long way, okay? This is a times a times a. That's a cubed. This is a times a, that's a squared. Okay, this right here is b times b times b, that's b cubed. And here is b times b times b times b, that's b to the 4th power. This, we can see this in action here. A cubed times a squared is the same as a to the 5th power. I have 5 a's being multiplied right here. Once I write this out the long way, there are 5 a's. So then a to the 3rd power times a to the 2nd power is equal to a to the 5th power. And we can see the same thing here. B to the 3rd times b to the 4th is the same as b to the 7th. And we end up getting the same answer. If you have questions, please leave your comments and I will answer them as quickly as I can. And if you haven't already, please subscribe. Thank you so much for watching, and we'll see you next time for part 3.